Hello and welcome. My name is JP Metcalf, and today we're going to go over an ENVI deep learning tutorial called Extract Multiple Features. The first thing I'm going to do is go to the L3 Harris Geospatial website, which is l3harrisgeospatial.com. And the second thing I'm going to do is go to support, come down to self-help tools, tutorials, and then I'm going to scroll down until I find ENVI Deep Learning Tutorial, Extract Multiple Features. Go to the second page. And then I'm going to put this into a new tab. And then I'm going to scroll down to figure out what imagery or data sets I need. And it says that the sample data files are available on our ENVI tutorials page. Click the deep learning link. I'll go back, and on the right-hand side, ENVI tutorial data. And the fifth one down is deep learning. If I click this, I assume I'm going to be downloading a zip file. It's about 1.3 gigabytes. And while that downloads, I'm going to open up ENVI. And go over a little bit about what some of the material is going to talk about. So in this tutorial, you will use ENVI Deep Learning to create a classification image showing different types of property damage. And this is all from the damage from a tornado. You will learn how to use regions of interest, ROIs, to label different features in imagery, and how to train a TensorFlow deep learning model to learn those features in a separate but similar image. The tutorial can be used with ENVI Deep Learning 1.1 or later. I'm currently on Deep Learning 1.2, and the steps may vary when using 1.1. So this was made when 1.1 was out. Some system requirements is that you need an NVIDIA graphics card with compute capability between 3.5 and 8.5. And we suggest having at least 8 gigabytes of video memory. The steps for this tutorial were successfully tested and created with ENVI Deep Learning 1.2 using an NVIDIA GTX 1070 with 8 gigs of memory and a driver version of 471.11. So if you have above that, everything should work. The sample data files are available on our ENVI tutorials page, which we just pulled. And then we're going to extract the contents to a local directory. I'm in my downloads folder. Right-click ENVI Deep Learning Tutorial Data. And I'm going to extract this. Okay. Look inside. 3 folders: object detection, shipping containers, and tornado. We're going to be using the tornado folder. And it looks like we have training raster 1 through 4 and its associated ROIs and header files, of course. And then lastly, we have an image to classify. So these images are subsets of the public domain emergency response imagery of Joplin, Missouri, tornado in 2011. Images are courtesy of the National Oceanic and Atmospheric Administration, NOAA, National Geodetic Survey, NGS, Remote Sensing Division, and they're available at storms.ngs.noaa.gov. Real quick, I just want to see what that website looks like. Storms.ngs.noaa.gov. And I have a bunch of hurricanes here. And then there's a Joplin, Missouri tornado 2011. And if I click on that, I should be able to go into like the web served version of the imagery. And then now I can see with all the imagery mosaicked, it's like a WMTS layer, that I can see like a path of the tornado. So the imagery that we're using is from this website. The images have 3 bands, red, green, and blue, at a 1/4 meter spatial resolution, 0.25 meters. They were exported to ENVI raster format for the tutorial. Spatial reference information was added to each image based on the information from the source JPEG world files. And the original images were acquired from an airborne Emerge/Aplanix digital sensor system, or DSS, on 24 May 2011. Okay, so we have 5 images, 4 for training, 1 for classification. And then we have 4 ROIs, which are going to be the labels for the imagery. We also have a trained model. Right here it says trained model.h5, and that's to we're going to give you an already made model, so you don't have to go through the entire steps of creating it. So let's go over some of the background. A common use of deep learning and remote sensing is pixel-based feature extraction, which we're doing today. That is, identifying specific features in imagery, such as vehicles, road center lines, or utility equipment. Through a process called labeling, you mark the locations of features in 1 or more images. And with training, you pass the labeled data to a deep learning model so that it learns what the features look like. Finally, the trained model can be used to look for more of the same features in the same images that we trained on, or in additional or newer imagery. This is the classification step. So a typical workflow is with the labeling, you're basically saying, here are the features that I'm interested in. In training, we want it to learn what the features look like. And in classification, we want to find more features like this elsewhere. You can train the deep learning model to find all instances of the features, for example, conducting an inventory of assets, or to draw approximate boundaries around the features. In this tutorial, you will train a deep learning model to look for different levels of structural damage from an EF5 tornado in Joplin, Missouri. It occurred on 22 May 2011. The tornado killed 158 people and caused damages that totaled $2.8 billion, making it the costliest tornado in U.S. history. According to the National Weather Service, nearly 7,000 homes were completely destroyed and 875 homes suffered minor to severe damage. Aerial images captured after natural disasters like this can reveal the extent of property damage and changes to the landscape. Visually inspecting images and marking locations where damage occurred can take a significant amount of time for an analyst, especially if the damage covers a large geographic area. This can further delay the time it takes to issue insurance payouts so that the rebuilding can begin. Machine learning can be used to quickly identify areas from imagery that suffered various levels of property damage, which can help inspectors determine specific locations to focus on in the field. Deep learning is a more sophisticated form of machine learning that can excel in scenarios like this, where the distinction between damaged roofs and structural deterioration can be confusing in aerial imagery. ENVI deep learning uses TensorFlow technology, which is based on a convolutional neural network, or CNN. It looks for spatial and spectral patterns in image pixels that match the training data it was provided. Specifically, this tutorial uses pixel segmentation approach to training, as opposed to object detection. The first step in training a deep learning model is to collect samples of features that you want the model to find, a process called labeling. In this tutorial, you will train a deep learning model to look for different indicators of structural damage, which will result in a classification image with multiple classes. Okay, let's get ENVI up. So now we're going to start labeling training rasters with ROIs. To begin the labeling process, you need at least one input image from which to collect samples of the features you're interested in. These are called training rasters. They can be different sizes, but they must have consistent spectral and spatial properties. Then you can label the training rasters using regions of interest. The easiest way to label your training rasters is to use the deep learning labeling tool. And to use that, let's follow these steps. I'm going to start ENVI, which I have up already. Otherwise, go to the Start menu. I'm going to scroll down to ENVI 562 and then open ENVI. I have it up already. In the ENVI toolbox on the right-hand side, we're going to expand Deep Learning folder and double-click on Deep Learning Guide Map. And the guide map shows up, and it shows that we can go down a pixel segmentation route, object detection route, or if I hit overview, it's just going to give us some information about this module. So the ENVI help. The guide map provides a step-by-step approach to working with ENVI Deep Learning. It guides you through the steps needed for labeling, training, and classification. Click the following button sequence. So we're going to go pixel segmentation, train a new model, train a multi-class model, and then label rasters. Little widget comes up saying this tool will save all of your changes and edits as you go. There's no need to manually save your work. I'm going to hit OK to get this out of the way. We have a little labeling tool here. And it looks like we're going to have our class definitions on the left-hand side and then our training rasters on the right-hand side. So to set up a deep learning project, we're going to use this labeling tool. And projects help you organize all of the files associated with the labeling process, including training rasters and ROIs. They also keep track of class names and the values you specify for training parameters. So we need to go to the directory where we save the tutorial files and then create a subfolder called project files. So I'm going to go back to my Windows Explorer, and inside of here, I'm going to make a new folder. And I'm going to name this project _ files. Perfect. This should be a new folder, nothing in it. So in the labeling tool, if I go to File and say New Project, under project type, I'm going to ensure that it's pixel segmentation. And because we went down the deep learning guide map portion, and we said that it was going to be pixel segmentation, it restricts us to just this. If I were to just open the deep learning labeling tool on the right-hand side, it would give us an option between object detection and pixel segmentation. So in the project name, I'm going to name this Tornado Damage. And then in the project folder, I'm going to hit this little ellipsis, go to my downloads, open up the tutorial data, and then Tornado. And then I'm going to point it at project files and say select. Now, if this was a folder that had something in it already, it would complain and say this folder is not empty. Since we just made it, I'll hit OK. And now we have some extra information. It says pixel segmentation, and then the project name is Tornado Damage. When you create a new project and define your training rasters, ENVI creates subfolders for each training raster that you select as input. Each subfolder will contain the ROIs and label rasters creating during the labeling process. The next step is to define the classes you will use. Use the class definitions section, which is on the left-hand side, to define the features you will label. The feature names determine the class names in the output classification image. Click the Add button in the lower left corner of the class definitions section. Okay. Little green arrow is the Add button. And the first definition that we're going to make is roof damage. So I'm going to type in roof damage. Little green check mark should be okay. And then we get a default color of red. What we want to do is change that to yellow, and I can do that by clicking the red color. Then I'm going to select one of these main ENVI colors at the top. I'm going to select yellow. We're going to add another feature called structural damage. Hit OK. Then we get that default red again. And instead of red, we're going to change this to orange. Let's see if we can find a better orange. There we go. The next one, the third one, is going to be rebel. Hit OK. Rubble is going to be red, so we can leave it there. And then the fourth class is blue tarps. Let's leave that a blue color. Very characteristic of after event imagery, or after hurricane, tornado, is to see blue tarps located on the rooftops of housing when rooftops can get damaged and you don't want water to leak in, protect it from the elements. All right. The next thing we're going to do is select the training rasters we want to train. So in the rasters section, we're going to hit add. And then a data selection dialog comes up. And what we're going to do here is look for the bottom. It says open file. So the data selection assumes that we're looking for data that we've already opened in ENVI already, which we haven't yet. And to open data in ENVI for now, we're going to open file at the very bottom. You can go back to go up a level and go to our tornado folder. And then we want training rasters 1 through 4. So if I hit control or hold control, I should be able to grab training rasters 1 through 4. Hit open. It'll open each. And now we have our 4 rasters, and I want to open all 4. I'm going to hit select all. And we can see that there are 3 of 3 bands, red, green, and blue. I'm not going to make any other changes here. And I'm going to say OK. The training rasters are added to the rasters section of the deep learning labeling tool. The table in this section has 2 additional columns, classes and label raster. Each class table cell shows a red colored fraction, 0 out of 4. Each training raster has 4 associated ROIs because you specified 4 classes. The 0 means that none of the 4 ROIs has been drawn yet. The label raster column shows a red color indicating no, that we haven't created label rasters yet. So a label raster is, it's going to take these original 3 band rasters and add a 4th band that will be the labels. Now we are ready to label the features in our training rasters by drawing ROIs in them. For the first part of the exercise, you'll learn how to draw polygon ROIs around examples of structures that have varying levels of damage. The labeling process often takes the most amount of time in any deep learning project. It can take several hours or even days, depending on the size of the images and the number of features. To save time in the second part of the exercise, you will import the ROIs that were already created for you. So, to save time, let's import those ROIs. So in training raster 1, I'm going to have it highlighted, and I'm going to come down to this little cogwheel, and I'm going to say import ROIs. And you remember they're already made for us. So I'm going to match that up with training raster 1 ROIs for training raster 1 and hit open. And then a new dialog comes up asking, all right, we see roof damage, structural damage, rubble, blue tarps in the ROIs. Do these match up with what your class definitions are? And it's a 1-to-1 match. We'll hit OK. It loads the image. It'll show the ROIs. You can already tell how long this might take to be able to manually label this. Little ENVI information dialog comes up saying the ROI tool is activated now. That means that we're labeling. The ROI tool's up, and it says that we have a record count of 54 just for roof damage. So if I selected structural damage, we'll have a record count of 28. Rubble, 32. And 35 for blue tarps. Okay, and now our classes say 4 out of 4, that we have labels for each one of the classes that we defined in our definitions. Let's close this, and we're going to do the same for training raster 2. Import ROIs. Select open. Ensure that there's a 1-to-1 match. And click OK. In this subset, it looks like there's a lot of damage actually. ROI tool has been activated. And then our ROIs are come back in. I'm going to close the ROI tool, and it says we just have training raster 2 in. I'm going to hit draw just to bring those ROIs in so I can look at them. All right, it looks like the roof damage and structural damage ROIs have a basic roof shape. And then some of the rubble ROIs are kind of maybe blobs. Kind of hard to tell that it was the actual roof. And that makes sense. If I wanted to look at this more clearly, if I highlight region of interest, I can change the transparency. And then I can see what the engineers of this tutorial document thought were associated with each class. Okay. That's training raster 2. Let's get the third one in. Import ROIs. Ensure that we're using training raster 3. 1-to-1 match. Hit OK. Here's our fourth raster. Third, excuse me. And again, our ROIs didn't load automatically. All I have to do is hit draw. And this looks like it's maybe just outside some of the main damage. I can hit zoom to full extent. And it looks like I'm already there at the full extent. Let's get the fourth one in, and then we'll start looking at the statistics. Training raster 4, import ROIs. Hit OK. Then again, ROIs come out. I'm going to close the ROI tool. And then I'm going to hit draw, just so I can look at the ROIs. Okay. I can turn the ROIs off, on. And it looks like a considerable amount of time has went in to labeling these classes with these 4 different training rasters. Now that we have each one of the images labeled, if I come back down and highlight training raster 1, if I click this cogwheel or the options, I can show the labeling statistics. We can to view information about the current project and how much labeling was performed. So after hitting the project statistics, we can see that there are 4 classes, 3 bands, red, green, and blue, and 4 different training rasters. And then it's going to break down the information, make this larger, of how many shapes were drawn for each of the rasters. Information like this might be important if you have a rule of thumb of, before I train a deep learning model, I need to have at least 100 examples. And let's say it's for your organization. And we can tally all these up to figure out, if we meet our threshold. 100 is just a number I picked. But in general, when you're training a deep learning model, you want to give it as many examples as you can. We're going to close this. We've labeled all of our training rasters with ROIs. The next step is to train the deep learning model. Training involves repeatedly exposing label rasters to a model. Over time, the model will learn to translate the spectral and spatial information in the label rasters into a classification image that maps the features that was shown during training. Inside of the labeling tool, we're going to click Train, and then the Train Deep Learning Model dialog will appear. In between here and opening this up, I noticed that we don't have label rasters yet. What I can do, if I close this real quick, I can do that manually by hitting Options, Generate Label Rasters. This would have done this automatically after going into the Train dialog and setting up a model training. But you can do it manually just in case, because as you're labeling, if I were to add another label, it would say label raster no, or not yet, because I would have to generate a new label raster after adding training. I just want to have everything green here on the side just to make sure that I have what I need. So I'm going to hit Train. And at the very top, we have patch size. That parameter is the number of pixels along one side of a square patch that will be used for training. And if we keep the default of 464, that'll be fine for this. And then we have little information down here. It says larger is faster, larger patch size, but uses more memory. The training and validation split percentage. That slider lets you specify how much data to use for training versus testing and validation. Keep the default value of 80%. So 80% of our 4 rasters will be selected for training, while the remaining 20% is used for validation. And with the shuffle rasters turned on, means that each time that we train this, it'll be a different set of training and validation. And what we want to do is turn that off. It's really only a bigger deal if we train another model after this. The next 6 parameters, numbers of epochs, patches per image, loss weight, are advanced settings for users who want more control over the training process. For this tutorial, we're going to use the following values. In the number of epochs, we're going to change from the default of 25 to 20. The number of patches per image is set to 100, so we don't have to change that. For augmentation, scale, and rotation, we'll leave those as the default yes. For solid distance, we want 0 for all classes, which is default. For blur distance, we're going to set all to the same value of 1 to 8. And the way to do that for all of them is there's a little button that says set all to the same value. And I'm going to enter 1 to 8 and hit OK. The blur distance basically adds a blur to the label, and it lets the deep learning model train on blurrier versions of that class. And it helps when you're using different, when you're using the model on imagery that's similar, but it may be just a little bit blurry, which happens with the orthomosaic process. For the class weight, we're going to set the minimum to 0 and the max to 3. And the loss weight, we're going to set that to 0.5. And the last section is we're going to name our models. So we have 2 models that we're outputting. One is the best performing model, and the last one is the last model after 20 epochs. So I'm going to browse, and in project files, actually, no, I'm not going to put it in there. See, we have a trained model already. And what I'm going to do is name this train model. And to differentiate it, we'll say that this is the best.h5. And for the last, I'll give it a similar name and say that it's last. Once I hit OK, we're going to start training. So I'm going to hit OK. And we have a little dialog that says initializing deep learning. As the training actually begins, a training model dialog reports the current epoch number and the associated validation loss for that epoch. We're computing a few different things before we get into the training phase. Once we start training and we have a number of epochs, a tensor board dialog is going to come up in my web browser. And that's going to describe our loss and our accuracy. So if I hit refresh, I can tell that our model hasn't started yet. So if we're on the first epoch, we're not going to have any accuracy metrics yet. We're going to wait till it gets to epoch 2. So training a model does take a significant amount of time due to computations involved. Processing can take several minutes to half hour to complete for this tutorial, depending on your system hardware and GPU. If you don't want to wait that long, you can cancel this whole training step and use that trained model that was given to you. So we're epic 1 out of 20, still waiting for a loss metric to come in. I know that if I were to refresh TensorBoard, I have some older models. So it looks like these are still older. Okay. But a little bit about this. TensorBoard is a visualization toolkit included with TensorFlow. It reports real-time metrics such as loss, accuracy, precision, and recall during training. And we can always refer to the TensorBoard online documentation for details on its use. But in general, we want to watch accuracy improve, the loss to decrease, the precision to improve, and the recall to improve. Let's check our status here. Epic 2 out of 20, and we have a loss of 1.4. So we should be able to go back into TensorBoard and hit refresh. And I have a new trained model down here. And we're seeing that the accuracy is getting up to 94%. And this is for the batch. We have two different types, batch and epic. After the first few epics are complete, let's click on the epic validation loss, in TensorBoard to expand this section and view a plot of the loss values for each epic. So we want epic validation loss. Remember, we're only on the first epic right now. A value of 0 represents a perfect fit. The further the value from 0, the less accurate the fit. Loss plots are provided per batch, as in batch loss, and per epic, both for training and validation datasets. Ideally, the loss values reported in epic loss plot should decrease rapidly during the first few epics, then converge towards 0 as the number of epics increases. It's also normal to see spikes in loss during training. Epics are listed along the x-axis beginning with 0. So let's see where we're at. I'm going to refresh real quick. And after 3 minutes, we're on epic 3 out of 20 with a loss of 1.4. So we should have a lot more information per batch than we have per epic. So at the very top, we were looking at batch accuracy. What about epic accuracy? So we don't have as many data points in between, where the batch is calculating those metrics for the entire amount of batches per epic. Over time, it'll show 20 epics. And we're going to wait for training to finish and then note the point on the epic val loss plot at which the lowest loss value occurred. In this example, in the actual trained model that was given to you, the best model was made at the 19th epic, or a value of 18 on the x-axis. I'm going to turn off my camera and we're going to come back once this model has been trained. So I'll see you soon. And we're back. We have just trained a model on the 4 training rasters that we have. And as this has gone by, I've been watching the training metrics. And it turns out that if we refresh our tensor board, let's see, we have batch accuracies going up, batch loss going down. What we really want to look at is the epic validation loss. And I'm seeing numbers that are kind of high. And it says that our best model had a value of 0.73 at step 13. And overall, our model took about 26 minutes to train. But if we go to the tutorial data or the write-up, it shows that their epic validation loss was all the way down to 0.05. So what we're going to do is we're going to use that trained model to do the rest of the tutorial. So what we're going to do now is I'm going to minimize my web browser, and I'm going to close my labeling tool. What's cool about the labeling tool is everything that we did, it's saved every step that we've done. So if I had to come back and train a new model, like I said, we had kind of high loss values. If I go back into project files, I have the training rasters 1 through 4, a JSON file detailing where to find these rasters. And inside, there'll be a label raster, that's what the LR is, the ROIs that we imported, and then the source raster.json just explains where we're getting this information from. So if I close this, I can always come back, especially if I want to come back and add labeling. Like I said, that trained model was a little bit different than what we have. So I'm going to close everything that we have. I'm going to go into our data manager and get rid of these trained rasters, or at least close them, not get rid of them. Because what we're going to do is take that trained model and classify the image to be classified, the one that wasn't used in training at all. So everything that we're going to see from this, the model's never been exposed to it. So we have a model that was trained to find examples of property damage in 4 training rasters. We're going to use that same model to find similar instances in a different aerial image of Joplin. And remember, we're going to use the model that was given to you already. This is one of the benefits of ENVI deep learning, is you can train a model once and apply it multiple times to other images that are spatially and spectrally similar. Spatially and spectrally similar being that this image is from the same data set. So it's the same resolution. It's from that same website, storms.ngs.noaa.gov. So what we're going to do is we're going to open that last image, and it's called image to classify.dat. I hit open and it's going to appear in my main window. I'm going to resize the data manager a little bit so it's not so much in the way. So if I pan around this image, I can see significant damage. Let me zoom out a little bit. I can see blue tarps. Completely destroyed buildings, let's call that rubble. So what I would expect after passing this image past our trained model, that these blue tarps would be identified and labeled on a pixel basis. In this area, we have completely destroyed buildings. We get a little bit further south, and it's maybe minor damage, a few blue tarps here and there. But we're going to find most of our rubble here in this area. Real quick, I want to view the entire extent. This is what we're going to classify. The path of the tornado is visible as a lighter shade through the middle of the image. That sounds right. So in the deep learning guide map, we're going to click classify raster using a trained model. I just closed it. So here's an alternative. If I open up deep learning, pixel segmentation, and then I open up TensorFlow pixel classification, this will bring up the dialog. So you can do things sort of out of order. You don't have to use the guide map for everything. But if I did use the guide map and I went back into pixel segmentation, remember we were in train a new model and it asks us to label rasters. All I got to do is hit back twice, and then we're going to classify a raster using a trained model. So, but it puts in the image to classify, which we have in our data manager already. So in our input trained model, I'm going to find the trained model.h5. Remember, we made best and last, but looking at the metrics, they're a little bit different from what the original tutorial data was classified on. Excuse me, the original model. I'm going to hit OK. And right below it, it's going to say the name is tornado damage, and that it's trained on 3 bands and has 4 classes. I'm going to hit this full info real quick. And it says that this was trained in 2019. It's 2022 now. There are patches per epic, patches per batch, 20 epics. That's what we did as well. Class weight 0 to 3. And now we have some information. Blur distance. And then there's metrics in here that we can, you know, if we gave it to somebody else, like right now we're ingesting a trained model, so we're trying to find information about it. And let's see, there should be 20 values here. So validation loss at the first epic is 0.27. And at the very end was 0.19. Okay. Close this, but keep in mind, if you want to look at the information of a trained model, you can click this full info link. And now what we want to do in the output classification raster field, I'm going to go back to the downloads. Tornado. This is the classification raster. I'm going to name this Tornado Classification. .dat and hit OK. And in the output class activation raster, the activation raster is a little bit different than a classification image. It's basically pseudo probability that a pixel falls within a certain class. We're going to name that Tornado Class Activation. .dat. And for the display result, it's already by default not going to display it. We'll leave it like that. So once I hit OK here, it's going to reach out, grab that model, pass the image past it or through it, and then determine which pixels fall within those classes based on the trained model. Now this is actually processing on the GPU, similar to what it was doing with training. The process is not similar to training. It's just similar that it's using the GPU as well. We'll give it a second. A note here is that I'm performing this classification on one image, and that tool basically only wants one image at a time. There's a way to automate this process that I could run it on every single image if we pulled it from storms.ngs.noaa.gov, and then we can just classify the entire data set. But keep in mind, it does take a few seconds for an image of this size to be processed and classified. And we're almost finished. There we go. I'm going to minimize my guide map, or I'll just close it. Okay. So right away, without turning anything off or transparency, I can see that rubble and structural damage are really down this slope here, from my data manager to my north arrow. And I should be fully zoomed out. And then I'm going to uncheck the classified layer in the classification image. And now I can see the class image over the original red, green, and blue image. And if I toggle the classification image on and off, I can try to make sense of what we have here. Okay. I'm going to zoom in a little bit and maybe explore. I saw a bunch of yellow up here, which is roof damage. Let's just check and see if this is roof damage. Without knowing what this looked like prior, I mean, I do see some stress here. And not so much in the residential area on the right-hand side. And I can see the blue class scattered about. So if I turn off blue tarps, and then I zoom in here, you can see that our model picked up these blue tarps here. I'll turn it back on. There we go. Now, we have a class image, but if I wanted to create a shapefile of the classes for GIS analysis or presentations, let's do this. We're going to type vector in the search window of ENVI Toolbox. Vector. And what I want to find is classification to vector. And double click. I want to select the tornado classification.dat and hit OK. And then we're going to select all of the classes listed in export classes, which they're already selected, 5 out of 5. But then we're going to turn off unclassified. Which means since I just hit unclassified, it acted like that's the only one I want selected. So instead, I'm going to hit roof damage and hold control and select structural damage, rubble, and blue tarps. From the output method drop-down list, we're going to select one vector layer per class. In the apply symbology area, we're going to say no, which is default. In the output vector field, keep the default root name of classification to shapefile.shape. And it looks like in my instance, I don't have a default root name. So I'm going to write in classification to shapefile dot shape dot shp and click save. Then we click OK. And we're going to convert this classification image, everything except unclassified, to shapefiles. And this option may take a second or a few. Okay. Now what we're going to do is we're going to turn off tornado classification, and then we're going to open that shapefile, or there should be a bunch of shapefiles. We're going to open all of them. So I'm going to select the shapes, and I'm holding control while I do this. And some of them get pretty large. There's 4 shapefiles, and I'm going to select open. Okay, now I can see the outlines. The default colors are different than those of the classes and ROIs. We can change those. So if we double click classification to shapefile, blue tarp, double click. On the right hand side of the vector properties dialog, click inside of the line color right here. And we're going to select blue and apply. And in the background, I just saw that my shapefile is blue now. And what I want to do is, I closed that a little bit too prematurely, is I want to click the line thickness from 1 to a thickness of 3 and hit apply. A little bit larger now. Keep in mind that when you change the properties of a shapefile or any other vector format, they only persist in the current ENVI session. To avoid having to reapply properties of the shapefile each time you start ENVI, you can save the property symbology to a file on disk. When ENVI reads and displays the shapefile, it'll automatically apply the symbology. To save the symbology for this shapefile, click Symbology dropdown, and then save/update symbology file. And then ENVI will create a file called classification to shapefile _blue_tarps.evs in the same directory. Now we're going to click OK. And you know, I want to see if that actually worked. So I'm going to get rid of that in the data manager. I'm going to open my blue tarps again. And right now I see that EVS file right here. And then we have our symbology. Now we're going to do this for the remaining shapefiles. Roof damage will go to yellow, and all of the line thicknesses will be 3. Double click. I had a warning about how many records it had. Line color, I'm going to change this to yellow. Line thickness 3. Hit apply. I'm going to save the symbology. File saved. Rebel. Rebel's blue now. We're going to change it to red. Line thickness to 3 again. Apply. And then we're going to save the symbology. And then last, we have structural damage that looks to be orange. Yellow to orange. Hit apply. Save the symbology. Okay, let me zoom out a little bit, see what the impact of all this symbology is. Okay, we still see that a lot of red, which is rebel, structural damage down the path of the tornado, but we can see inside of those large areas as well. Another output of the classification process is a series of class activation rasters. Earlier in the TensorFlow mask classification tool, we created a file for activation, and each band of this file contains a grayscale class activation raster whose pixels indicate that the probability of belonging to a specific feature is going to be one of the bands. In this case, it has 5 bands: unclassified, blue tarp, roof damage, rubble, structural damage. So we're going to follow these steps to view the activation rasters. We're going to right click on each shapefile in the layer manager and say remove until we get back to where only the image to classify is in the layer manager. Oh, excuse me. Remove. There we go. And in the data manager, we're going to open the activation image. Tornado class activation, which is 1.5 gigabytes. And then now that it's in the data manager, we're going to select roof damage and then load as grayscale. At the bottom of the ENVI application in the status bar, right click in the middle of the segment and select raster data values. Right click, raster data. So now that when I move around with my mouse or cursor, it'll interactively show the data values for this activation image. So bright should be higher, and things should be from 0 to 1. So basically, how to interpret this is that a pixel with a bright value closer to 1 has a high probability of belonging to the roof damage class. To better visualize this, we can apply a raster color slice. And a color slice divides the pixel values of an image into discrete ranges with different colors for each range. Then you can view only the ranges of the data that you're interested in. In the layer manager, I'm going to right-click Tornado Activation and then click New Raster Color Slice. And the input file is roof damage. And hit OK. And it applies a default color slice. In the layer manager, we're going to uncheck the activation layer to hide it. Did that. And then in the raster color slice layer in the layer manager, uncheck the purple color slice range. That's the background. Here we go. The remaining colors, blue to red, identify pixels with increasing probabilities of matching roof damage. Let me close this. According to the training data, the remaining colors, blue to red, identify pixels with increasing probabilities of matching rooftop damage. According to the training data you provided, the following image shows an example, which is what we're looking at right now. So I'll zoom in a little bit, and we'll find high probabilities of a roof damage. There we go. And I can see that there's some areas that they show up as a color, but they're maybe not exactly roof. This area right here, and that's fine. It has a low probability. Now this area right here with the red, if I uncheck the raster color slice, it'll show that there is indeed a roof there and that it's damaged. Let's check out one more of the activation. Let's find rubble. Load as grayscale. I'm going to turn off the raster color slice for roof damage. And I'm going to back up to view the entire extent. We can see a black and white version of high probability of rubble, which we have a trend. And if I say new raster color slice for rubble, we have this default color slice that's adding. And if I hit OK and turn off the very lowest class, and then I turn off the activation image, I should be able to overlay the high probabilities of rubble against the original image. Okay. So for final comments, in this tutorial, learned how to use ENVI deep learning to extract multiple features from imagery using polygon ROIs to label the features. ROIs provide a quick and efficient way to identify all instances of a certain feature in your training images. Once you determine the best parameters to train a deep learning model, you only need to train the model once. Then you can use the trained model to extract the same feature in other or similar images. For further experimentation, consider running the ENVI modeler model file named deep learning randomized training.model. This model is provided with the ENVI deep learning installation. This ENVI model performs a full automated ENVI deep learning workflow multiple times, each with a different set of randomized training parameters. Each result is displayed separately so that you can decide which training run produced the best TensorFlow model. For more information, see the randomized training parameters section in the train pixels segmentation models topic in the ENVI deep learning help. Real quick, I'll show you where that's at. In the deep learning toolbox and a deep learning guide map, under tasks, under tools, there is randomized training parameters using the ENVI modeler. And what that's going to do is open up ENVI modeler in that .model file that will have some parameters inside of there that will randomize things like class weight or blur distance, things like that. In conclusion, deep learning technology provides a robust solution for learning complex spatial and spectral patterns in the data, meaning that it can extract features from a complex background regardless of their shape, color, size, and other attributes. For more information about capabilities presented here, please refer to the ENVI Deep Learning Help. And that's it from me. Thanks for joining.